So the Calc 1 chain rule review that we're doing here, let's do this composite y equals x squared plus 7, just for fun, to the 5th power. That's a function where you're going to need the chain rule in order to take the derivative. So the way that you probably learned it in Calc 1 is they broke it down for you. They said, oh, let's let u be what's inside the parentheses, the inner function, if you will. And then df dx, where y is equal to f of x, is equal to df du times du dx. So you did it sort of in parts. Well, what do you mean? Well, if we rewrite y as u to the 5th power like that, if we let u be the inner function x squared plus 7, then df dx is df du, but you're going to use the power rule on that. That's 5u to the 4th times du dx. But if u is equal to x squared plus 7, what's the derivative of x squared plus 7? Somebody, quick, tell me.
2x.
2x. Thank you. And then you're almost done. There's one more step they made you do when you took Calc 1, is like your final answer should only have the letter x in it, because that was your independent variable there. So you're supposed to back substitute and go, okay, what was u? Let's put him back in. And he was the quantity x squared plus 7. And then they usually wanted you to clean it up also. 5 times 2x is 10x, just to make it look nice and simplified, and then we're done. And so this was your derivative, we'll call it y prime, using the chain rule. So another way I want to look at this, because we're going to be looking at diagrams, tree diagrams essentially, is the diagram for this df dx is equal to df du times du dx would look like this. You have your function f at the top, y equals f of u essentially, which is a function of x, okay? So, you know, ultimately. So you have him, he's the parent, and then you have u here, and then underneath u, you have x. So when you're taking the derivative, so when you're getting df dx, you go down the tree. So you go on this branch, and this branch says, go take df du, okay? And then you multiply that by the derivative with the next branch in this tree. So to get from u to x, this branch here says take the derivative of u with respect to x, and then you're done, and then you got your chain rule happening, and then everybody's happy. So you're going to see that this little review is going to help you understand the chain rule here in Calculus 3. So it's going to be pretty intense. So there are 2 cases for the chain rule that we're going to study in this section, and you're responsible for both on the quiz, which is opening up Sunday and due Monday morning, and also on your midterm and also on the final. And by the way, I want to say something about this chain rule. It is going to be one of the most powerful theorems that you learn this semester. Like, I don't let anybody graduate from my class, Calc 3, without having a very good understanding of the Calc 3 version of chain rule. Like, you should be allowed to graduate. Maybe some people get by, but. So the first type is if you have, we'll call it W, is a function of, let's say, 2 variables, x and y. It could be 3, though. I'm just trying to do something generic. Where x and y are functions of a single variable. A single independent variable. So that's going to be one case, and that's an easy case, and we'll do that one first. Now the hard case, number 2. So the second case we'll look at today is where W will still be a function of x and y, where x and y are going to be themselves functions of 2 or more variables. We'll stick to it easy and we'll say 2 for now, are themselves functions of 2 variables. 2, and I'm just going to put 2, and I'll put in parentheses or more. It could be bad. I'm going to give you problems where it's like hellacious, and you got to be able to handle it. Independent variables. And what do they name these independent variables? Sometimes they'll name them like U and V, which I think is unfortunate because we used U and V to name vectors when we were doing our module on vectors, but whatever. So that's how that's going to roll. So we're going to do case 1 first, okay? So good morning, everybody. Hope we're all here. Okay, so case 1, let W be a function of 2 variables, x and y. And again, that could change. Like this is just going to be a very generic, but you can jack it up at any time, and we're gonna. And if x is a function of t, and y is also a function of t, so t is an independent variable driving the bus, and we'll let those g and h are also differentiable functions of t, then w is also a function of t. And so he's indirectly related to the t. And this is similar to what you learned in Calc 1 with this diagram. You had up here your function f, and he was eventually related to x down here at the bottom of the diagram. X was the variable driving the bus that you wanted to end up with your final answer only having x's in it. Okay, so here's the deal. If somebody says, hey, I want you to take the derivative of w with respect to this independent variable time t, t is typically time, how are you going to get it? And you're going to go, oh, well, first I'm going to take the partial of w with respect to x. And if you watched my videos Monday, the partial derivative letter d, and I will dock you for notation every time I see you violate a bad notation, is it's got a d, but the d has what I call a melted stem. The stem of the d is not straight. This is important. Times, now this next derivative is going to have a straight stem d, dx dt, because x is a function of a single variable, and when you're doing derivatives for functions of single variables, like you did in Calc 1 and Calc 2, you get a straight stem letter d, plus the partial of w with respect to y times the derivative of y with respect to t. So notice again, I've got partial derivative notation here for the letter d's with the curvy spines, and straight stem letter d's when you're taking derivatives of functions of single variables. Okay, now the schematic. I'm going to show you 2 schematics here. I'm going to show you the schematic that is in Briggs, as well as most every calculus book, which sucks because I'm going to show you a schematic that's superior and that I'm going to use for the rest of the semester. And, well, I'll let you figure out if you think it's superior or not. Check it out. So the one that you're going to see in the text looks like this. W is the parent. He is a function of 2 variables for the moment. And then x is a function of time t, and y is a function of time t. Okay, I prefer the following schematic, which basically says the same thing as this textbook schematic, but it's better, and you'll see why. So you still have w, you got x and y. This time t down here that you see that both x and y are dependent on is really the same time t. It's not a different time for y and a different time for x. It's the same time driving the bus. So ideally, the better schematic is mine, because this t, which is your single independent variable, is the t that's driving the bus. And now I'm going to use this to put on the branches the derivatives that you need to take. On this branch, you have the partial dw dx, take the partial of w with respect to x, and then you multiply that guy with the x dt. So that gives you this first term in the theorem. And then down the other branch over here, so you're going to add to that the partial of w with respect to y times the derivative of y with respect to t. So there's the other term. So you have to add those 2 guys together to get your chain rule. So this diagram that I prefer, I didn't make this up. Dr. Arnie Vallone, may he rest in peace, my mentor at San Diego State, is the one that introduced me to this, and I thank him for that because I just think it's better. And when we get into more than one independent variable, you'll see that that my schematic or Dr. Vallone's schematic is just better because it just makes more sense. Okay, now if you do your MyMathLab, and I hope that you are, you'll see a similar thing here. They'll put dw dx here, and then dx dt along this branch, and then the partial of w with respect to y times the straight stem dy dt. Now for those of you who are like, oh, I don't care about notation, screw it. I don't care about these curvy stems or the straight stems, blah, 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 whatever. Yeah, you're going to get some MyMathLab problems wrong because they are specifically going to give you some of these weird diagrams. It'll be a multiple choice problem with lots of weird diagrams, and they'll purposely put wrong notation in the ones that are wrong. And if you go, notation doesn't matter, it's all the same to me, and then you pick the wrong diagram because you're not trying to get this notation for yourself. Okay, I'm going to do some examples. I'm going to first do, I'm going to do this problem two ways. The chain rule way, and then the sleazy way where you try to circumvent, not using the chain rule. And you can for these problems if you really want to, but there are ways of stopping you from circumventing. I have ways to circumvent the criminal mind. Okay, I stay up nights trying to circumvent the criminal mind. And I don't know if I mean, I don't catch everybody, but you know, I think that I'm not alone in finding that, you know, teaching online is a challenge, and I know learning online is a challenge. I get it. You got a lot going on, and it's hard to focus and concentrate on a teacher droning on and on about the chain rule. But you want to learn this for yourself, okay? So when it's time to take your exam, you want to know it, because when you get your degree and you go out in the world and you interview, you're going to be the one answering the interview questions, okay? Not your study buddy or someone else, okay? I just got another text from a colleague of mine who, again, you know, there's like, they gave a midterm and they had a whole bunch of cheating going on, and I said, well, I can relate, you know. Even in my programming class, I caught cheaters last week. It's all over the map, okay? Do your own work. Learn for you, because you're going to want to. Method one, how do you use the chain rule for this? So keep in mind, they're giving you a function of x and y. They're giving you x and y that are functions of time t. So if you go up here and you look at this diagram, you got w is a function of x and y. He's related to those. But x and y themselves are functions of t. So if you use the method one, the theorem says this is how you're going to get dw dt. That's what they want. You're going to first find the partial of w with respect to x. Then you'll multiply it with the derivative of x with respect to t, plus the partial of w with respect to y times the derivative of y with respect to t. So we're going to do this in slow motion, and then you're going to find at the end we have to back substitute. And then we'll, at the very end, we'll evaluate at t equals 0. For God's sakes, do not evaluate at t equals 0 at the beginning. Why not? They said to. Because then you're just going to get pure numbers everywhere, and the derivative of all pure numbers is going to be 0. And you're going to go, hey, the derivative is 0. And it's like, probably not. And in this case, it definitely isn't. Okay, so let's get the ingredients. I have to find 4 different derivatives. 4 different derivatives just to get the derivative of w with respect to time t. Good God. So let's get all of these pieces one by one, and then we'll put it all together. So what is the partial of w with respect to x? So that means you're going to look at w, and you're going to hold y constant. So this means that you're treating y like a pure number, like the number 2 or something. So what is the derivative of x squared y with respect to x? Y is just a constant, so he's just going to multiply along for the right, and you're going to multiply this constant multiple with the derivative of x squared with respect to x, which is 2x, minus what is the derivative of y squared with respect to x? Anybody want to try that one? Maybe you watched the video and you know how to do it.
0.
Good. Good, because y looks like a pure number, so y squared is a pure number, and so you've got the 0 there. So if I clean this up and make it look pretty, there's 2xy. Now what about the other partial? So now we're going to take the derivative of w over again, but we're going to hold x's constant. So it's going to look like x is a pure number, just temporarily. So what is the derivative of x squared times y with respect to y? Keeping in mind x looks like a number. Anybody want to try that?
X squared minus 2y.
Okay, x squared, yeah, I just wanted to know the first term. You're way ahead of me. And then the derivative of y squared is 2y. So we got that. And so we're done with that partial. Now let's get the other ingredients, the derivatives of x and y with respect to t. So the notation here is straight stem d's. So you're taking the derivative of x with respect to t. X is just a function of a single variable. That's when you know you have a straight stem. So everybody in the room should know what the derivative of sine of t is, because come on, that's like calc 1, and that's cos t. And then dy dt is the derivative of e to the t, which is e to the t. And then when I put all these ingredients together, my dw dt is going to look like this. Dw dx, which is 2xy, times dx dt, which is cosine of t, plus the partial of w with respect to y, which we got is the quantity x squared minus 2y, parentheses matter. And you're going to multiply that by dw dt. Now, I'm only going to give you half credit if this is what you put. I don't even think my math lab will give you any points. Why not? Because your final answer is only allowed to have the letter t in it. Well, how come? Because t is the one that's driving the bus, and you're taking the derivative of w with respect to time t. So I don't want to see any x's and y's in here. Oh, I'll just replace x's and y's with t. No, you won't. That's not legit. You're going to go back to what x and y were defined as in terms of t and simply back substitute. So what I mean by that is your dw dt, if I do this, you're going to have 2 times x times y, but x is sine t, y is e to the t, and then you also still have the cosine t factor, plus, and then you're going to have this quantity x squared minus 2y. Okay, that's going to be sine squared t minus 2e to the t, and you're going to multiply that with e to the t. I'm going to clean this up just a little bit, just because I can. If I, rewrite some stuff here, this looks like 2 sine t cos t e to the t. Okay. If I distribute this e to the t over that difference, I'll have e to the t sine squared of t minus 2 e to the 2t. Now I can evaluate dw dt at time t equals 0, and I'm just going to substitute 0 everywhere I see a t, and that's not going to be too hard. And then what is our final result here? Well, sine of 0 is 0, so 2 of those terms just go to 0. Beautiful. And the only term we have here is the negative 2e to the 0, and so your final answer is negative 2. So the rate of change of w with respect to time t is negative 2. Fine. So I just finished method 1. Now, what if I did this all over again using method 2? So let's do method 2 on the next page because I'm running out of room as usual. And that's why I put blank pages in your course reader there. So if you run out of room too, you can go look at your blank page. Okay? So method 2, I'm not really a fan of because you're basically trying to avoid using the chain rule altogether, which is kind of like not fair. But it works. So method 2 looks like this, is your w is x squared y minus y squared. But they told you that x is sine t, so just do some substituting right here, and y is equal to e to the t. So your w is this function here, and now you can see that w is a pure function of the single variable, independent variable t. So if you had to find dw dt here, this is just a calculus 1 problem. You don't have to use the math 252 chain rule. And for those of you who are like, yeah, that's the way I'm going to roll, I got news for you. Like I said, I know how to circumvent the criminal mind, as you'll see in the next problem. You will not be able to do this for the type of problems that I like to give on quizzes and exams. You'll see. Okay, so let's just do this, the brute force method. How would you take the derivative of this first term? What derivative rule would you need? Good, product rule, excellent. So you have a product rule here. So if I call the first factor f, the second factor g, I'm going to need f prime g plus g prime f. I'll do this pretty quick. F prime, the derivative of that exponential is just e to the t times g, we've got sine squared t. And then when you take the derivative of sine squared, you're going to need the chain rule from Calc 1, 2 sine t, cos t, and then f is still e to the t. And then minus, and now it's easy to take the derivative of e to the 2t power. That's just going to be 2e to the 2t. And I'm done. Now, you may be thinking, wow, that was, and of course, dw dt evaluated at 0 is still going to be the -2. And you may be thinking, wow, this was way easier than doing the other way. I don't hear empty water bottle while driving noise. Are you driving, David?
No, right now.
I don't know.
That's Rasky riding on her
Yeah.
Surface Pro.
It's probably my Surface Pro, which is a piece of crap. I apologize. I don't know. It's like, oh yeah, there is a fan. Yeah, I have a fan on.
Oh, there we go. Yeah.
Yeah, and I'll tell you why I have a fan. Because my Surface Pro sucks. Did I mention that recently? Because it rolls hot. And because it's hot, I have it on this cooling stand. I don't know if you guys can see this setup I have here. And so it's these, I bought it online. You can, it's like $40. And it sits here and it helps it from overheating. Yeah, new technology sucks. Okay. So I apologize if it sounds like, a wind tunnel or something. That reminds me of some stories my dad told me about some wind tunnels when they were testing, but that's for another day. Let's keep going. All right. Now, when's the chain rule come in handy? Well, here we go. Now, you may remember some of these problems from Calculus 1. Do you guys remember related rates by any chance?
Yes.
Oh my God. I just got a flashback. Wow.
Yeah. If you just got like, oh, God, help me from Calculus 1, related rates where they go, oh, okay, this is changing with respect to time. How much is the cube changing with respect to time? I mean, I've taught Calc 1 multiple times. One of my favorite related rates problems that I love teaching in Calc 1 is, somebody skips a stone across a pond. And I don't know if you ever skipped a stone across a pond. Have you ever seen like the ripples of the water that make concentric circles, and the concentric circles move out, outward and get larger and larger? And then they'll ask you like, oh, what's the rate of change of one of these circles radii, or the radii of these circles with respect to time? At the instant, one of the radii is equal, the outer radius circle is, 2 feet or something. Do you remember something like this?
Yes.
Yes.
You're going to do that right now in Calc 3 on steroids. Congratulations for making it this far. But you need the chain rule to do it. Without the chain rule, you can't do it. And here we go. I'm going to do, this is a 2-part problem, mainly because about 5 years ago, I only used to do part A in my lecture, and then I would give part B on an exam. And then I get a lot of tears, like, oh, I don't know how to do surface area of a rectangular box. And these people couldn't even do it. I was like, ah! So I'm going to do it for you, just in case you see it on a quiz or exam. So here you go. We have a rectangular block of ice, and it's melting, okay? And it's got some length and width and height. And when the length is exactly 9 feet, it's a big block of ice, okay? And the width is 8 feet, and the height is 2 feet. These variables are changing, okay? The rate of change of the length with respect to time is -1 foot per hour, so it's melting. The rate of change of width with respect to time is -2 feet per hour, and the height is decreasing at -1/3 feet per hour. So, letter A, what's the rate of change in the volume of the block of ice? I hope you can imagine that the volume is definitely shrinking, so we're probably going to get something negative. We better get something negative. And you want to make sure you give correct units also, because, that's going to be part of the problem. So it looks like they're giving feet, and volume is going to be feet cubed, and then the rate of change with respect to time. So this is what they're asking us to get. What is the rate of change with volume with respect to time? What is dV dt equal to? That's what they want to know. I'm going to draw a diagram because it helps. You've got your volume function at the very top. He is related to these three variables, L, W, and H. So it's a function of three variables. Oh, yeah. But all three of these variables are all related to time. They're functions of a single variable, time. Time's driving the bus. So that diagram can help you get dV dt. Watch closely how I use the diagram to help me so I don't screw up. So the volume is changing with respect to time. You're going to go down this first branch and you're going to find the partial of volume with respect to the length. And then you're going to multiply that by this branch, which is dL dt, the rate of change of the length with respect to time, which, by the way, that is a derivative, but they gave it to you. So when the time comes, you're going to actually plug in to that dL dt, -1 foot per hour, but not yet. Plus, because I want to see this on your paper first. Then you're going to go down this branch of our little tree diagram. You're going to take the partial of v with respect to w times, and then you're going to go down the next branch to get to your time, dw dt, the rate of change of the with respect time, and they also gave that to you so you don't have to actually go and get a derivative for this guy. Cool. And then the last variable we got to handle is the partial of volume with respect to height. Cool. So, so if I put all the little derivatives down each of these, because you'll see this on a tree diagram, you know, they'll put these on all these derivatives. So dv dh, that's a partial. So you got those melted stem d's, they got to be curvy, and then times dh dt with a straight stem d. And there's your derivative of volume with respect to time. Oh my God, we got 6 derivatives we got to go get. But good news, we only actually have to get 3 because the dL dt, the dw dt, and the dh dt are provided to us. They actually gave those values. So now let's go get these partials, and we'll do it on the fly. So the derivative of volume with respect to time is the partial of v with respect to L. Well, what is the volume of a rectangular box? So what is the volume with, you know, in relationship to the H and the L and the W? Does anybody know how to find the volume of a box?
You
If you
multiply
don't, we
those
can't do
three.
the problem. Go ahead.
Do you multiply all those three together? The
Exactly, exactly. Thank you. So you've got, you know, L, W, H. It doesn't matter the order. So there's your function of 3 variables. That's the guy that's at the top of your tree diagram. Okay, beautiful. Now go take that guy's partial with respect to L. So what does that mean? You put on a special set of glasses, and when you look through these glasses, both W and H look like pure numbers. So what is the derivative of LWH with respect to L? Anybody want to try that?
WH.
Very good.
WH.
WH, just the constant multiple. And then you're going to multiply that by dL dt. And we'll get to that in a moment. Plus, now let's go get the partial of volume with respect to W. So let's go once again to your function LWH. What's the derivative of that guy with respect to W? You're going to hold the L and the H constant.
LH.
Good.
LH.
Right? Very nice. And then you're going to multiply that by dW dt. So excuse me, that should be dV. No, that's right, dW dt. Plus, and now you're going to go get the last partial. You're going to take the partial, the last one, take the derivative of volume with respect to H now. What should you get?
LW.
LW. And then you multiply him by the dH dt. Now it's time for substituting. Yay! So you're all set because they want this volume's rate of change with respect to time when W and H and L are all constant. So you're going to have WH, so that's going to be like 8 feet, and then you multiply that by height, which is 2 feet, and then dL dt was -1 feet per hour, plus LH, so that's going to be 9 feet. Oops. I hate this Surface Pro. Somebody get me a new computer. Somebody. times h, okay, that's 2 feet. And then they gave dw dt, which was, what was dw dt for crying out loud? It was negative 2 feet per hour plus, and then L times W. So L, I believe, was 9 feet. And then, sorry, that didn't come out so well. And then your W was 8 feet. And then you're going to multiply that by dH dt, but that's negative 1/3 feet per hour. And then you whip out your calculator, and I get, after punching all these numbers up, negative 76. What are my units?
Feet per hour?
Careful. Look at one of the terms. You notice I'm multiplying feet times feet times feet per hour?
Cubic feet per cubic hour.
Cubic feet per hour.
I almost said cubic hour. Uh-oh.
No cubic hours here. But that would be a nice concept. Okay, so I'm done with letter A. Thank you very much. Does anybody have a question?
I'm good.
Okay. What is this about? Oh, cubicle warning. Okay. EPA assassins. Right. We got to watch out for those guys. Has anybody seen Ghostbusters, the original? You know, probably before you were born.
Yes.
You remember the scene where, it's kind of toward the end of the movie, where I think it's the EPA who comes in to inspect the Ghostbusters lab, and Dr. Venkman, that would be Bill Murray, you know, says, yeah, come on in and sit down. And he's like smoking, back in the day when people smoked in movies, and he's got his feet up on the desk, and he's basically trolling the EPA guy. I love that scene. Anyway, I digress. Let's get back to letter B. So letter B I gave on a quiz like 4 or 5 years ago, and most of the class flunked because they couldn't figure out what the original volume was. But I claim that this diagram is still going to be the diagram we're going to do business with, but now we're going to talk about surface area. So the surface area, instead of V, we'll call it big S. It is a function of L, W, and H, but it's not L times W times H. You want to add up all of the areas of all 6 faces of your box. So does anybody know what the surface area is for a rectangular box? Quick.
Six LH.
Oh my goodness. No, not 6LH. All right, I guess we got to do this in slow motion. Listen up. Are you guys engineers? Are you guys physicists? Are you guys mathematicians? Because if you don't know geometry, Pythagoras had across his math academy, when, you know, the Greek guy, Pythagoras, the guy who invented the Pythagorean theorem, he said, it was a plaque across the door. It said, let no man enter who does not know any geometry, or something like that. Okay, he wouldn't let anybody into his math academy if you didn't have like the basics of geometry down, because you just don't have any business. That applies to you people. Now listen up. Here's how you get surface area. Let's take the front of the box. Does everybody see that this area is going to be WH, and there's going to be 2 of those faces for the front and the back? So you got 2 WH. Plus, now anybody want to help me out now?
2 WL.
LH.
2, oh yeah, so you're going to have 2, sure, WL, and then plus what? 2,
LH.
yeah, 2LH, thank you. So that is a surface area formula for a rectangular box. You should know this and love it. If you don't know it, I don't know what to do. Like, I can't help you get some of these formulas you're supposed to know already. It's a crying shame. I was trying to help a Calc 2 student last week, and we were trying to do some of these. Have you guys ever remember something like tangent, cosecant inverse of, I'm just going to make something up. This is one of their quiz problems. You don't take a derivative of this. You just give the expression. It's a trig problem. Well, this person did not know the Pythagorean theorem, like at all. Like, I even just try to go back to basics, and the Pythagorean theorem is just not in this person's DNA. And it was troubling because this person is in Calc 2. I hope that's not you. You're not in my Calc 2, but if you don't know the Pythagorean theorem, dear God. Okay, So how do you do this? Well, folks, if they want the rate of change of surface area with respect to time, we want ds dt. So you're going to take the partial of s with respect to one of the variables, say L, and then you're going to multiply that by dl dt, plus the partial of s with respect to w, and then you're going to multiply that by dw dt, plus the partial of s with respect to the last variable, that would be h, times dh dt. So there's your guy. So do we have to get all 6 derivatives? No, because in this problem, and we're still working on the same problem, they gave us the LDT, DWT, and DHDT. That was nice. We just have to get these 3 partials, and they're going to be different from the volume derivatives because this is a different function. So you'd be very careful that you do these correctly. So what is the partial of this surface area formula, but with respect to L? That means you're going to hold W and H constant. Now, since W and H are constant, like the number 2, what would be 2WH's derivative with respect to L?
2WH?
No, 2WH would be a pure number.
0.
W and H are
Zero.
constant.
Oh, right, there
Thank
we
you.
go.
The derivative of a pure number is 0. Yes? So that's not even there. I'm not even going to bother writing it down. And now let's take the derivative of the other 2 terms with respect to L. So the derivative of
2W.
2WL is 2W. The derivative of 2LH is 2H. And you're going to multiply that by dl dt. And we already know what dl dt is. It's negative 1 foot per hour. Plus, now you're going to start over. You're going to get the partial of S, surface area function, with respect to W. So you're going to put on a different set of glasses, and it's going to look like the other variables. The L's and the H's are pure numbers. So you're going to take the derivative of the first term, 2WH, with respect to W, I believe that's 2H, plus the derivative of 2WL with respect to W, that's going to be 2L. And then the last term's derivative is 0, because that's just a pure number in the eyes of the variable W. And then you multiply that by dW dt, and then ds dh. Okay, now this last partial, you're going to hold W and L constant. So the first term's derivative, the derivative of 2WH with respect to H is 2W, plus the derivative of 2WL with respect to H is what?
W plus 12.
2L.
Okay, let's just look at this middle term. What is the derivative of 2WL with respect to H?
0.
Thank you. Okay, and so then the last guy is going to give us 2H, and then you'll have DH dt. Okay, and now it's just time to plug stuff in. So you're going to go ahead and everywhere you see dl dt, you'll put negative 1 foot per hour.
You mean that the last one gets a 2L?
The last?
A 2L, thank you. Sorry, 2L. So you're just going to do a whole bunch of plugging in, and so I'm just going to do quick. I'll factor out a 2 here, 2, and these are supposed to be feet, 2 feet plus 8 feet, so that's going to be feet, and then you'll have negative 1 foot per hour plus, and I'll factor out a 2 here, and then I'll do H plus L. I think that's 2 feet plus 9, so that's going to be feet. And then the dw dt was negative 2 feet per hour. And then finally, I'm going to have 8 plus 9 feet. I have no idea what I'm writing. I'm writing invisible ink because this is very delayed. Negative 1/3 foot per hour. Punch it all up. And then my calculator says negative 226 thirds. Negative 226 thirds. What are the units now? Be careful. This is not volume. We're finding the rate of change of surface area per time. What would that rate's units be?
Feet squared per hour.
Good. Feet squared per hour. Very good. Thank you. And we're done with that problem. Let's move on. I'm going to skip the next problem because I don't have time, because I want to get to it. I'll just give you the answer. And for those of you who want to do this problem on your own, this is very similar to what I'm going to put on the quizzes and exams, so do it. It's the answer here is letter D. And they're giving you the surface area for a right circular cylinder. The trick for this one is that a lot of students bomb this problem is because they're not paying attention. They're telling you that the radius is increasing at a rate of 9 inches per minute. So this is going to be a positive number. Then they're telling you the height is decreasing at a rate of 7 inches per minute. So the dHdt is negative. And so if you blow this, then the whole problem goes down the toilet because you screwed that up. Okay? So that's a little tip for that problem. Let's move on to case 2 because I got a lot to do today and time's wasted. So we're now at case 2. So if you recall, I started this lecture at the very beginning with the 2 types of chain rule that we're going to look at. And one of them, which is where you have a single independent variable, I'm done. Let's do second type. Second type is where you have a function that has more than one independent variable. So it gets a little messy. I'm just saying. And your tree diagrams start looking pretty messy. So you have to like keep it all straight. And if you're a fan of tree diagrams, I am. I'm a big tree diagram girl. It will definitely help you. Speaking of tree diagrams, for anybody who takes probability, and you do a little bit of probability if you take a stats class like Math 119, if you're going to basically help yourself, if you've got some massive probabilities going on, draw a tree. It's great. There's other ways to do it, but if you're smart, you'll draw a tree. Okay. So let's do the case 2. So we're going to start off easy and then we'll get a little bit more messy. So we'll start off easy, meaning let's say the function w is a function of only 2 variables. That could change. That could be 3, 4, 5, 6, who knows. And those 2 functions themselves, the x and the y, those guys are going to be functions of 2 variables, let's say u and v. And let's say you have all these partials you got to worry about, dx du, dx dv, dy du, and dy dv. Let's say they all exist. Then this guy here is going to need 2 partials. He doesn't have any straight stems going on in this whole problem. All of the letter D's have curvy spines. So you're going to have to go get dw du, and we're also going to want to worry about dw dv, because the u and the v are the independent variables that are driving the bus. So dw du is going to be the partial of w with respect to x times the derivative of x with respect to w, so that's another partial, plus the derivative of w with respect to y, that's a partial, and multiplied by the partial of y with respect to u. The other partial derivative for w is going to be with respect to v. You're going to still need the partial dw dx, so these are sort of repeats here, times, but now you're going to multiply him by the partial of x with respect to v. That's a v, not a u, plus, and then you again have the partial of w with respect to y, which is kind of like a duplicate from the other guy, times, but you're going to multiply by the partial of y with respect to v. Now, I love schematics because they're awesome. So let me show you the schematic from the textbook, which again sucks. And then I'll show you mine, which I think is superior. Although, you know, you're not going to see it in the textbook or in my math lab. So here's what you'll see in the text. W is a function of 2 variables, x and y. And x himself is a function of 2 variables, u and v. Okay, and there's the tree diagram that you'll see in the text. And if you want to put the little partials here, you'll see dw dx here, and then down this branch is dx du, that's a partial, and here's another partial of x with respect to v. Down this branch, you'll have dw dy, and down here you'll have the partial dy du, and down this branch you'll have the partial of y with respect to v. Okay, and you can kind of see how these partials here in the theorem come to be. So if you're going to find dw du, you go this branch times this branch, so you get to the u, and plus this branch times this branch, so you get to a u also. And then the v is similar, but you try to get down to your independent variable v. So for this guy here, I'll use a different color. You still got to go down this branch. That's why you see that guy showing up in both of the formulas. But then you multiply him to get to your v. And then the plus the dw dy times dy dv. So that's kind of thing. Now my personal favorite, I prefer this diagram instead, because it's just more apropos for what's happening. You still have w as a function of two variables, x and y. And both x and y are functions of two independent variables, u and v. And the u's and v's are really the same guy. Like this diagram, what I don't like about it in the text is it makes it look like this u and v over here is different from the other pair of u and v. Like, well, they're totally different from each other. They don't even talk to each other. No, they're the same guys. So why not show that? It shows that my diagram shows it better like this, because it shows that x is a function of u and v, and y is a function of the very same u and v. So I just prefer my diagram, but that's how I roll. But you won't see my diagram in your homeworks or the text, so just to let you know. But I prefer it because it really tells more of what's happening. You got the drivers of the bus down at the bottom. Okay? So using the chain rule for a function of more than one independent variable, let's go do some problems. Okay? So I could do this way one and way two, where I do all the back substituting at the beginning and then circumvent having to use the chain rule altogether. I just go ahead and take partials, knowing how to take partials. Okay. I don't know, is my internet going wrong, Nicholas? I don't know. Don't know what
I
to
guess
say.
you're fine. I mean,
Just try to do the best you can, okay? All right, so let's do the chain rule to do example 4, and then we'll do example 5 and 6, and then we'll get to implicit differentiation, and hopefully we'll wrap that up today. So on the quiz this Sunday, remember I'm going to make it 200 points. There's 5 problems out of the 15 that are taken from section 15.3, partial derivatives. I'm going to ask you how to get partial derivatives, you know, and maybe some second partials in there thrown in the mix. So know how to do that. They're pretty basic, but again, you know me, how I roll, I like the product rule and the quotient rule and all those other things in the mix. So know how to do partial derivatives with that added layer of complexity on there, because that's, you need to know how to do that. Then I'm going to give you like 5 problems that have to do with the chain rule, and then 2 that have to do with implicit differentiation, which we're also going to do today. And then the last few problems, rounding out all 15, are going to be Friday's stuff on directional derivatives and gradients. So that stuff's pretty intense and super important. So don't even think about not being here. Okay, chain rule. Here you go. You got a function w that is a function of x and y, and you can even tell by looking at it. It's got x's and y's in it, fine. And x is a function of u and v, and y is also a function of u and v. So there you go. So if we're going to go get dw du, we're going to first get dw dx and then multiply that by dx du, plus dw dy times dy du. And there's 4 derivatives I got to go get there. Okay, let's do this. And we'll do it in slow motion. So first, let's get the partial of w with respect to x. So that means look at this function, e to the x multiplied by sine y. How would you find the partial of e to the x sine y, but with respect to x, keeping in mind that you're holding y constant, so sine y also looks like a constant multiple. Yep, very good, Emily. It is e to the x sine y. Nice. And then you're going to multiply that by dx du. Okay, well look at what is x? X is u times v squared. How would you take the partial of that with respect to u? That means you would hold v constant.
E squared.
Just v squared. Nice. Okay, we're done with that guy. Plus, now go get dw dy, the partial of w with respect to y. So you're going to hold x constant. How would you differentiate e to the x times sine y with respect to y?
EX cos.
Yep. And then I'm going to multiply that with dy du. So you're going to look at y, which is u squared multiplied with v. And what is the derivative of u squared v with respect to u?
2uv.
Very good. Now you're not done, because this is a hot mess. It's got X's and Y's and U's and V's in it, and you're not allowed to leave it like that. Why not? Because we're taking the partial with respect to those independent variables, you only want to see the independent variables in your final answer. And so the ones that are driving the bus, in this case, my diagram above on the previous page, I only want to see U's and V's in the final answer. If I see any X's or any Y's, you're dead. Well, how do I get rid of the X's and Y's? You just back substitute. Like, what was X? Everywhere you see an X, you'll substitute UV squared. And everywhere you see a Y, you'll substitute U squared V. So it's going to look pretty gross. Like e to the X is going to become e to the UV squared. I know, weird. Times sine of Y, but that'll be sine of U squared V. Times, you'll still have times the V squared going on there. Plus, and by the way, you want to clean this up. Like, I like my algebraic factors in front of my transcendentals just because. In fact, let's just put this crap in the beginning. Let's look, 2UV, just put that there. Times, and then e to the x, that's e to the UV squared, times cosine of Y, but that's cosine of U squared V. And you're done. So this is the partial of W with respect to U. It's this big mess. Okay. Go get the other partial. All right, well, the other partial, if I use the theorem, is dw dx times dx dv plus dw dy times dy dv. And these are all partials. Now, the good news is we already got the partial of w with respect to x, and we already got the partial of w with respect to y when we did the previous partial. So I'm just going to sort of put that in there. But now we need to worry about taking the partial of x with respect to v. So go back to what x is. It's defined as uv squared, and take his partial with respect to v. And you should get, yep. And then the dw dy, and then times dy dv. Well, if y is u squared v, what is the derivative of u squared v but with respect to v?
Square.
U squared, good. And then I don't accept final answers that have all these letters in it. You're only allowed to have the independent variables, which in this case are U's and V's. So, clean it up and start, I would put this in front because it looks pretty. You'll have e to the uv squared times sine of y, but that's u squared v, plus u squared e to the uv squared times cos of u squared v. And we're done. I'm not going to factor out anything. I mean, you could factor out common factor. Don't bother. But you're done. So here is the other partial of w, but with respect to v. And it looks pretty gross, but that's a lot of times how these partials look. Okay. I will pause there for questions.
I'm good.
Okay. So this last problem is a problem I always love to put on exams and quizzes when I teach this course, because it just messes people up, because it's got a lot going on, and because they don't really know what's going on, they blow it. But if you keep your ducks in a row and you have nice tree diagrams, everything comes out in the wash, and there's really not much to do except know your chain rule, because they give you everything. So there's no derivatives to take because they're giving you values. So here's the deal. They're starting at the top. Z is a function f of xy. And by the way, the hard part about this problem, I'll just tell you in advance, so I'll give away the secret. All these functions they're going to give you have two different names. And as long as you keep the track of all the names, you'll be fine. And you probably can appreciate this. I know some of you have different names, nicknames you have for your friends, right? A lot of your friends probably don't call you by your legal name, like some of you guys, what you call each other, bruh, or whatever. So that's your other name. But then you got too many people named that. That's going to be a little bit of a problem. We can't have 17 people named bruh. So the partial derivative looks like your number 2, Nicholas. You better clean that up, because when I grade and I see 2s all over the place, I'm going to go, what the heck are you doing with the number 2? What's up with you and number 2? Sorry, I got to hit the stop button for a moment. No, wait. All right, so let's go back to this. Okay, who does number 2 work for? There's your z equals f of xy. So in other words, he is a function of 2 variables, x and y. So you may want to start your diagram. You have to be careful because remember, everything is 2 names, and this is going to be the trick. So x is also going to go by his nickname g, and that g is a function of 2 variables, s and t, and y is a function of 2 variables, and his alternate name is h. Now, s and t are the independent variables, and they're the ones driving the bus. So both x and y are dependent on those 2 independent variables. Okay, here's my diagram. Now, they're saying everybody's differentiable. Okay, we're all happy. When s and t are known, so s is some number 2 and t is some number -1, then what do we know? We've got the function g is equal to a value, and you don't care about what the g is really doing. You're like, okay, g is equal to, g evaluated 2 -1 is 3, but that's neither here nor there because it's not a derivative. But gs, now this subscript notation I also go over in those partial derivative videos I made for you. So g subscript s means dg ds. So when you're taking dg ds, that's this right here, gs is evaluated at the point 2 -1 is going to be a 5. So down this branch you're going to have that partial. Now the next info is gt, so that's another partial. That's the derivative of g with respect to t is equal to -3, they're telling us, fine. And now the next thing they're going, well, h is equal to 4 when s and t are 2 -1. That's fine, but it's not going to be helpful to us. It's like, okay, thanks for the info. But that basically gives you what x and y are doing. So this is, remember, that's x and that's y. And now let's go to partials. hs, that's the partial of h with respect to s. So that's going to go down this branch. The partial of, which is the partial of y, hs is going to equal 2, and then ht, that's the partial of h with respect to t, is -2. And they're also telling you, suppose that fx, that's along this branch, evaluated at the point when x is 3 and y is 4, and that's why they gave you these other pieces of info, they give you what x and y are, is going to be 12, so that's this branch here, and then the other partial, fy, when you evaluate x and y at 3 and 4, is going to be 7. Okay, fine. Now we're going to use the appropriate chain rules to get dz ds and dz dt. Okay, so if we use the theorem and we use the differential type notation, dz dt is equal to the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. But the alternate names and the alternate notation, you kind of have to know a lot just to do this problem. Otherwise, even though it's pretty easy, this is the same as fx. And this is the same as gs, because the alternate name for x was the g function. Plus, dz dy is the same as using the notation f subscript y, and dy ds, since y's alternate name was h, that's hs. So now you're just going to plug in all the values because they told you all the values of all of these partials at the point that they want to find the partial. So you're going to go, okay, fx is 12, gs I think was 5, fy was 7, and hs was 2, and then this is going to be, what, 60 plus 14. Final answer, 74. We don't have any units because this is a kind of a unitless problem. So the point is, this is dz dt is 70, excuse me, dz ds is this was supposed to be an s here, my apologies, I put wrong notation. Dz ds is 74. So we got half the problem. Now they want dz dt. Okay, so dz dt is going to be dz dx times dx dt plus dz dy times dy dt. Now I'm going to tell you a little secret, and I didn't want to tell you this right off the bat because I don't want people like so getting into this. But if you look at this notation here, and you sort of like, if you could cancel these things with each other, which you kind of don't want to do right so much, but you'll notice that dz ds is equal to dz ds plus dz ds, and that should work out okay. if you're doing all the proper stuff. And then we're gonna, again, we're gonna use the alternate notation. This is the same as the F subscript X notation times, this is GT, this is FY, and this guy is HT. And then you just plug in all the values, and FX is still a 12. GT was what, -3, plus FY was the 7, and then HT was a -2. And then without the calculator, or do the math in your head, I get -36 minus 14, so I get -50, and this is dz dt partial. Okay, and we're done with that problem. And I love giving that problem because it tests a lot of things. It tests if you know your tree diagrams, alternate notation, and all that stuff, all in the same problem. So it's not really hard, but it seems like it's really complicated, more complicated than it really is. Okay.
Are you going to be expecting tree diagrams during exam?
No, but I would encourage you to use them so you stay out of trouble. Yeah?
Yes.
Okay. So I'm sorry your friend didn't pass his DMV test, David. Passing the DMV test used to be harder than it is, because back when I had to take it, you had to parallel park. I understand that they took parallel parking off the table now, and you don't even have to do that. Nice. Okay.
Even though he just got his license, we still make so much fun of him for being the last one of our friend group to get their license.
Well, a lot of people don't have licenses these days because a lot of people don't want to drive, which I think is odd, but because that was like a rite of passage when I was a kid. You know, all the bad boys had cars. Okay, everybody take a look at the tree diagrams. Look at all these tree diagrams. Oh my God, this looks like a disaster zone. So you're going to do two things for this one problem. By the way, I just took a screenshot of this from my math lab. So this is going to be a problem probably you're going to see or something like it. So don't, don't laugh too hard, but you got to get it right. So what are they saying? They want you to get, a dy dc. C is going to be some independent variable. So they're telling you that y is a function of r, s, and t. Okay. And that r is going to be a function of one variable only, just c. And s is going to be a function of two variables, b and c. Interesting. And then t is going to be a function of three variables, a, b, and c. Oh my God. So look at all these diagrams, and how, let's try to figure out if we can figure out, which of the tree diagrams is correct first, and then we'll do dy dc afterwards, because the dy dc doesn't help us or not help us to figure out which tree diagram is correct. Your knowledge of them telling you who's a function of how many variables, this and that, is going to be the way you'll pick the correct tree diagram, as well as maybe some notation. So I want you guys to look at letter A. Letter A is definitely not it for a few reasons. So I'll go over why through process of elimination, letter A is not the case. Look at one of these branches here. Do you see what that says? It says dr over dy. No. That should be what on that branch? Bad notation. Somebody help.
dy over dr.
Very good. That should be dy over dr. And similarly, this should be what?
That's dy over dt.
Yes. And then this also should be dy over ds. Okay, so that's right then and there, you're out. Like bad notation, no way. The other thing is, r here, that's that guy there. You see how it looks like he's a function of three variables, a, b, and c? That's not correct. He's supposed to only have one variable he's a function of. And similarly, the middle guy, the s, that's this guy here, from this diagram looks like he's a function of a, b, and c, and he's only supposed to be a function of b and c. So those also tell us a is not going to work. Okay, let's turn our attention to b. Is he going to be the guy? It looks like at least this notation is good. So that's an improvement. So we like the notation there. But why would letter B still not be a good choice? Anybody want to?
R has three
It's supposed to only have one.
Yeah, R should only have one independent variable. Should only have one independent variable. And it looks like from this diagram, he's got 3 attached to him. So that's no good. How about letter C? Is letter C a good candidate?
It's bad notation.
No.
Bad notation again, like not good. So bad notation, yucky. That should be dy over dr. This should be dy over dt. This should be dy over ds. And then similarly, this should be dr over dc. Okay, so you got to make sure you have your notation not upside down. Okay, so that this is no good. This is no good. This is no good. Guess what? Letter D is the correct choice. So this is by process of elimination, but that is the correct choice. Here you have R as a function of 1 variable, S as a function of 2, T is a function of 3, and they have the correct notation. Everybody's happy. Okay? Now, how about the correct chain rule below? So which one of these chain rules, oh my God, this is a hot mess, is the correct chain rule to find dy dc? Remember, they want dy dc as our goal for this for these choices here. So does anybody see a choice that looks like it's going to do the job?
I have no idea.
B?
Who said that?
Like it.
Me.
I said
Emily,
B.
you are correct. Letter B is correct. Very good. Now, folks, when you look at these, and you know, I hear somebody said, I have no freaking clue. And somebody asked me like 5 minutes ago, hey, do we have to draw these trees? You know, this is like really a bore. Yeah, but if you draw the tree, maybe you won't screw up. Like, look, you want dy dc. So you go look at the correct tree. First, you get dy dr, and you multiply that by dr dc. Boom. Plus, then you go down another branch, dy ds, multiplied by ds dc. Aha. You always try to get to the c's. And then finally, your last branch, dy dt, times dt dc. And that kind of, that taking you down your tree branches there gets you to the correct formula. And I will dock you if you don't put correct formulas on your paper for your handwritten uploaded work on Sunday, even if you have the right answer. Like, well, I got the right answer, you know, I punched in all the right numbers. Yeah, but I want to see like formulas. I want you to show me that you know this chain rule, that it's all good. It's not that hard. So we're done doing the chain rule. Congratulations. And now let's do implicit differentiation. Any last questions on chain rule?
I'm good.
Okay.
So for the quiz, are you going to want us to do something similar to these tree branches and all that stuff?
Well, that's what another student asked. No, you don't have to draw trees. But if I do want to see formulas, and so if you're still not clear on the formula, I encourage you to draw the tree in order to make sure you have a good formula.
Okay.
I don't know if that answers your question or not, but you know, if you're still confused about, like, if you looked at all these formulas and you went, oh my God, I have no idea, then that's when I suggest you draw a tree.
How is partial derivatives applied in the real world?
How do partial, oh my God. Take a physics class. Okay? They're all over the place. So, you know, I can give you like a, I'll give you a biology problem to answer that. I mean, there's so many different possibilities, but let's say you had a bunch of, well, let's do coronavirus. Let's say you had some virus in a Petri dish here. I don't know how to draw coronavirus, okay? And let's say that these coronaviruses, you're trying to, you know, you're in one of those Wuhan labs and you want your coronavirus to grow. So what are some things that might affect it? What are some things that would affect your coronavirus? I don't know, temperature, maybe, you know, nutrients. I'm just giving some different variables, okay? There might be more than that. You know, what are some other things that might encourage the coronavirus to grow? Does anybody have an idea?
H, maybe?
What is H?
Human.
Okay.
No, I'm just trying to grow them in a petri dish. Okay. Yeah, it may be light. Okay. So let's say these are three variables. Call them T, N, and L. And so P will be our function. The population of coronavirus is dependent on temperature, how much nutrients it gets, and light. Now, I'm not talking about coronavirus in people. Sure, the people that tend to get very affected tend to be elderly and, you know, have comorbidities. But let's just say we're trying to grow them independent of people. Now, do you see this as a function of three variables? What if I want to check how does the population of coronavirus get affected if I want to increase the population? And let's say we're going to change the temperature, but we'll keep nutrients and light constant. So we'll hold the amount of nutrients we give it at some constant level and the light at a constant level. And we'll look at the rate of change of the population of the coronavirus with respect to the temperature, T. Does this make sense? I'm just trying to give you an idea of how partials are in the real world. Like, and this is just one example. I could go on and do all sorts of examples. Like, for those of you that take chemistry, you know, PV equals nRT, all you chem people. Hello?
Yeah.
Oh, yeah. So you could solve for any one of these variables. And if you don't know the PV nRT formula, go take a freaking chem class, okay? But I could solve for any one of these variables, and then that one quantity would be dependent on the other quantities, and then I could examine the rate of change of that quantity where I hold most of the other quantities constant and just vary the one. You see what I'm saying? That's partials in action. You could do it for all kinds of things. You could do it for the economy, because the economy is dependent on unemployment rate, tax rate, and all sorts of other variables. And then you could examine as an economist, what's the, you know, how does the economy do if we hold everything constant except for the tax rate, you know, and then examine that, although that's still a dismal science. Okay, let's do implicit differentiation because we can't. So I'll at least start it and then we'll wrap it up on Friday. But Friday is going to be a hell of a lecture, so don't be late. I'm just going to roll right in. I'm going to do I think I'll do my announcements 5 minutes in advance and then get to it. So don't be late. It's Friday. Okay, so let's do some review from Calc 1. So you maybe remember in Calc 1, and this may bring up some bad memories, but if you don't understand the Calc 1, then you won't be able to understand the Calc 3. You may remember that they gave you some wacky looking function, like, ooh, now that is not a function of x. Like if you tried to graph it and run the vertical line test on it, not a function of x. Does not pass the vertical line test if you did graph it. However, it does have a very beautiful graph to it. And, you know, certainly we could graph it. Like I could go to my graphing calculator here. Let's see if I can find it. Here we go. And which allows me to put in some wacky stuff here. So I'm just curious. Y cubed plus y squared. You know, when I teach Calc 1, I do this kind of stuff for the Calc 1 groupies there. And I know you guys are all graduates of Calc 1, but if I gave you a Calc 1 final right now, do you think anybody could really pass it? And I'm talking about a Rasky final. Okay. So check this baby out. Ooh, that is some funky looking graph. Can you guys all see that okay?
Yeah.
Okay. Can you tell that it's not going to pass the vertical line test?
Yeah. Yeah.
But here's the thing. I could pick a point anywhere on one of these funky curves, like, hey, right there, and go, hey, what would the slope of a tangent line be at that point? What would the slope of the tangent line be at that point? Or how about this point over here? Or how about this point over here? You know, what's the slope of that tangent line or this tangent line? So you can still talk about slopes of tangent lines, even though this curve is, you know, one big, you know, hot mess. And that was what they were trying to get you to see in Calc 1. You can still talk about the slope of the tangent line to a point. So the problem is, because you can't get this in explicit form, it's what we call an implicit function, you had to use the technique of implicit differentiation to get dy dx. So if you recall, you would take d dx of both sides of the equation. So I would d dx the left-hand side, and it is equal to d dx of the right-hand side. And this isn't partial differentiation, okay? In Calc 1, they don't teach you partial derivatives. You take the derivative with respect to x of both sides, where y, any term that has a y in it, you have to use the chain rule on it. So for example, the derivative of y cubed with respect to x is 3y squared times dy dx. Plus, the derivative of y squared is 2y times dy dx. I'm just using the chain rule. Plus, the 4xy, if you recall, needs the product rule. So you first take the derivative of 4x with respect to x, which is just 4, times y, plus the derivative of y with respect to x, but that's dy dx, times the other factor, which is 4x. And that has to equal the derivative of the right-hand side with respect to x. Well, the derivative of 1 is 0. The derivative of 5y is 5 times, using that chain rule, drill down into the inner shell of the y function, minus the derivative of x squared with respect to x is 2x. Now you solve for dy dx. Well, how do you do that? Very easy. It's now just an algebra problem. Get all the terms that have dy dx on the same side, everybody else on the other, and factor out a dy dx. So you'll notice we got a lot of terms that have a dy dx in it. We've got 4. And then this term here and this term here don't have a dy dx. So I'm going to move that guy to the other side by simply subtracting both sides by minus 4y. And I'll subtract this term from both sides to move him to the other. I'm doing a lot of steps all at once. And then when I factor out the common factor, which is the dy dx factor, and then solve for dy dx by simply dividing both sides by that big hunk in quantity, my slope at any point on my curve is this formula right here. So if you, as long as you pick a point that lives on that graph that I showed you, and you plug in the coordinates of that point into this formula, you will get the slope of the tangent line at that point. Does anybody remember this Calc 1 junk?
Yeah.
Okay, you are not to do that in my class. Like, we're not going to do this implicit differentiation. Well, why not? Because we're going to do it a quicker, dirtier way. It's much better. You're going to love this. And do not teach this to any Calc 1 students. If I hear about it, you're dead, okay? Seriously, they're not supposed to know about partials. But let me derive it for you, and then we'll do it, and then we'll finish out the problem, and then I'll do the rest of this. So the idea is, when you're handed one of these functions with x's and y's in it, that's this big honking equation right here, what you do is you get a different type of representation for it. You get everything in one side and 0 on the other. This is called the general representation. And we'll call that everything on one side w. So what you're going to do is you're going to move everything to one side, all the junk, and then it'll have equal to 0. And this stuff here, you'll call it w, which will be some big old function of 2 variables, x and y. And you're basically saying, well, that function of 2 variables, x and y, is equal to 0. Fine. Then, to get dw dx of this function w, you use the chain rule. And here's the chain rule in action. So, well, how do you do that? So you take fx, and then you multiply that by dx dx, which is just 1. You know, the derivative of x with respect to x is 1. Plus the partial of big F with respect to y times dy dx. And that has to equal the derivative of the right-hand side, because w is equal to 0. You're taking the derivative of both sides of this equation. But what is the derivative of 0 with respect to anything?
0.
Yeah. So now you've got this big old equation, and so solve this equation for dy dx. And that's very easy because you'll just subtract this from both sides of the equation, so you'll still have the fy xy times dy dx is equal to negative fx. And then dx dx is just 1. And then divide both sides by big Fy, and you have this formula. And this is the formula that you can use to get your dy dx. So I'm going to do the problem up here all over again. So if we go to the next page, and so I have this on the next page here, I just derived it. So here's the function of two variables, and then we'll do this Friday. But so I just derived this for you right now. So here's why this is so awesome. Let's do this calculus 1 problem all over again, okay? But we're not going to do it the calculus 1 way. The way you're going to do it is you're going to get this form. This is step 1. So I want to see this in action. You want to get all the stuff on one side and 0 on the other. It doesn't matter which side. It's all going to come out in the wash. I don't care which side. So how about if we just have everything, move everything over to the left. So when I move everything to the left, I get all this junk on one side and 0 on the other. Now this, folks, is your big F, and he's a function of two variables, x and y. So dy dx, if you use the theorem, is just, you're going to take the opposite of the partial of f with respect to x and divide that by the partial of big F with respect to y. Here we go. I'll just keep the negative out front. So let's look at this big mess. What is the derivative of that with respect to x? So that means hold y constant. So what's the derivative of y cubed with respect to x?
0.
0. And how about y squared?
Also 0.
Also 0. Now how about the derivative of 4xy with respect to x?
4x.
Careful, 4y.
Or y. Y. I'm
And
sorry.
then the minus 1 is 0, and then the minus 5y, that derivative with respect to x is 0, and then the minus x squared is what? Or that's supposed to be a plus, sorry.
-2.
That's a plus, sorry, I had to, when I moved him over, I had to add him to both sides. So it's going to be plus 2x. And this minus has to affect the whole thing, so we'll put parentheses around. And now, let's divide that by fy. So you're going to take the derivative of this big old function again, only this time with respect to y. So hold x constant. Okay, the derivative of y cubed with respect to y is?
3y squared.
Plus?
2y.
Plus?
4x.
And anything else?
Minus 5.
Very good. And you're done. This is the answer. I'm done. Now compare that to the answer that I got when I did it the calculus 1 way. Is that the same?
It's the exact same.
It's the exact same darn thing. Is that exciting or what? Everybody in the room should be saying the following.
Wow.
Wow is correct. So, good news. I'm done. I have office hours today at 12 noon. You're welcome to come. I encourage you to come. If not, I have to grade Math 130 exams. I still haven't looked at those yet.
Oh,
All
no.
day.
I try not to think about it because it just makes me cry. Okay, so I'm done. If you need to leave, see you later. Thanks for coming. Thanks for staying. I'm going to stop the recording. I'll stay a couple